All right, listeners, get ready. We're diving deep into the world of pentaquarks today.
Pentaquarks. Oh, yeah, those are fascinating.
They really are. And, you all sent in tons of research on these exotic particles.
It's some really mind-bending stuff. It challenges how we understand the universe, at the tiniest level.
Absolutely. And it's definitely a topic worthy of a deep dive. So let's break it down, shall we? We know atoms exist, right? Pretty basic.
Sure.
But if we zoom way in,
Right.
deeper than the atom,
Right into the nucleus.
exactly, you've got protons and neutrons and electrons doing their thing around them.
And even those protons and neutrons, they're not the most fundamental pieces. It's like those Russian nesting dolls. You open one and there's another one inside.
Ah, I like that. So what are those even smaller pieces?
Those would be quarks. 6 different kinds, actually. Up, down, strange, charm, top, and bottom.
Okay, so 6 quarks. And those are the tiniest bits, right?
Yeah.
The Lego bricks of the universe, so to speak.
Pretty much. And like Legos, they combine in different ways to make different particles.
So 2 quarks together, what do you get?
That's a meson.
And what about 3 quarks?
Now you're talking baryons. That's where protons and neutrons fit in.
Okay, I'm starting to see the picture here. 2 quarks, meson, 3 quarks, baryon. That's what we call the standard model of particle physics.
Our best understanding of how the universe works at that super small level.
Right, but then we have these pentaquarks. 5 quarks. And that's where things get weird.
It throws a wrench into the whole system. It's like finding a hidden room in your house, one you never knew existed.
That's a perfect way to put it. So were pentaquarks always part of the plan, so to speak, or did scientists just stumble across them?
The idea of pentaquarks has been around for a while, since like the 1960s, believe it or not.
Right, that long. But early theoretical models, they couldn't quite explain how 5 quarks would stay together in a stable way.
Yeah, it's only with newer tools like lattice QCD that we're making real progress.
Lattice QCD, huh? That sounds complicated.
It's a mouthful, for sure, but it's a really powerful way to simulate how quarks interact. Imagine a supercomputer, right? It's crunching numbers to see if those 5 quark combos are even possible.
Oh, wow. So these simulations predicted what pentaquarks might look like their mass,
Yeah.
before we even saw them in experiments.
Exactly. They laid out the blueprint, so to speak.
So you've got these theoretical predictions, but do they actually exist? I read that early experiments were a bit of a roller coaster, lots of ups and downs.
Oh, definitely. There were some initial claims back in the 90s, like an experiment in Japan called LEPS, and then Diana in Russia.
They thought they'd found pentaquarks.
They were hunting for this pentaquark called the Theta Plus, but other scientists couldn't replicate those results. That's a big no-no in science.
Right. You need that consistency to be sure.
Exactly. One experiment can't prove a whole new particle exists. You need confirmation, independent verification, the whole 9 yards.
And that brings us to 2015, right? The big breakthrough.
Yeah. LHCb at CERN, they announced solid evidence for pentaquarks. Finally.
The LHCb, that's the Large Hadron Collider, right? The one everyone's heard of.
The very one. And they have these super advanced detectors and the power of the LHC behind them.
So how do they find the pentaquark?
They were analyzing the leftovers of other particle decays, and boom, the signals matched the theoretical predictions for this pentaquark called the PC4450 plus Dalir.
So that pretty much confirmed that pentaquarks are real, didn't it?
Game changer. And suddenly we're not just adding a new particle to the list, we have to rethink things, like the strong force.
The strong force, that's the one that binds quarks together, right?
Exactly. And if it can bind 5 quarks, what else is possible?
That's the million-dollar question. It really makes you wonder what other secrets the universe is hiding.
For sure. I mean, if pentaquarks exist, why not particles with 6, 7, or even more quarks?
Ooh, my mind is officially blown. So the discovery of pentaquarks, it's not just adding a new entry in a textbook. It's challenging our fundamental understanding of physics.
Right. Absolutely. And it's only the beginning. Who knows what other discoveries are waiting for us out there?
Welcome back, everyone. We're in the middle of our pentaquark deep dive, and things are getting really interesting.
It's pretty mind-blowing stuff, right?
Totally. Last we left off, we were talking about that huge discovery in 2015 by LHCb.
Right, the PC4450 plus pentaquark.
The one that decays into a JC particle and a proton, if I remember correctly.
You got it. But here's the thing, that wasn't even the whole story.
What do you mean?
Well, LHCb actually found evidence for 2 more pentaquark states hiding in the same data.
Wait, so there were more pentaquarks lurking in there?
They were just harder to spot, really close in mass to that first one. It's like trying to separate 3 stars in a cluster. You need a really good telescope.
Ah, okay. So what makes these different pentaquark states unique? Besides their mass, I mean, is there something else that sets them apart?
Well, besides mass, each pentaquark has its own barcodes, so to speak. We call them quantum numbers.
Quantum numbers, like a particle's ID card.
Exactly. They describe the pentaquark's properties, things like spin, parity, isospin, all those fun physics terms.
Seems complicated.
It can be, but think of it like this. Imagine you have a box of Legos, right? But you can't open it. So how do you figure out what's inside?
You could shake it, listen to the sounds, maybe weigh it.
Exactly. Quantum numbers are like those clues. They give us information about a particle's inner workings, even if we can't directly see them.
That's actually a great way to think about it. So different quantum numbers mean different internal structures.
Right. And finding pentaquarks with different quantum numbers tells us there's a whole family of these particles out there. But figuring out the exact quark content of each one, that's a real head scratcher.
How do they even begin to do that?
It's like solving a cosmic jigsaw puzzle. Physicists look at the pentaquark's mass, its quantum numbers, how it decays. They compare all that to theoretical models, trying to figure out which quarks are inside.
So it's a detective story, basically. But then we have that whole debate about whether some of these pentaquarks are really five-quark states or something else entirely.
You're talking about the molecular hypothesis.
Right. The idea that maybe it's not a true pentaquark, but a baryon and a meson, two separate particles just dancing really close together.
It's a fascinating alternative, isn't it? Imagine two dancers, so close they look like one creature with 5 limbs.
It's like a cosmic tango. So how do we figure out who's right?
That's where the electron-ion collider comes in. The EIC is going to be a game changer,
We've mentioned the EIC a few times now. Why is it so important for pentaquark research?
Think of it like getting a high-definition camera for the subatomic world. The EIC will let us smash electrons into protons and neutrons with incredible precision.
So we can finally see what's really going on inside these pentaquarks.
Exactly. Is it a true 5-quark state? Or just a baryon and a meson doing a little dance? The EIC should give us the answer.
I'm actually getting goosebumps just thinking about it. But I have to ask, what's the practical use of all this? Like, why does it matter if a pentaquark is a true 5-quark state or a molecule?
Well, it's like any fundamental research. Sometimes we don't know the practical applications right away. It's about pushing the boundaries of knowledge, understanding the universe at its deepest level.
So the pursuit of knowledge is its own reward.
Exactly. And who knows, maybe understanding pentaquarks will lead to some incredible new technologies down the line. It's happened before, with things like electricity and quantum mechanics.
I can't argue with that. But for now, it's all about unraveling the mysteries, right?
Absolutely. We're still in the early stages of exploring this new frontier. There are so many questions to answer.
So what are physicists doing in the meantime? Waiting for the EIC to come online?
Oh no, they're busy bees. They're working on theoretical models, analyzing data, even using things like machine learning to help us understand these pentaquarks.
It sounds like the discovery of pentaquarks has really shaken things up in the physics world.
It's a whole new ballgame. And it's a reminder that there's so much more to discover, so much we don't know about the universe.
Okay, so we've talked about the different types of pentaquarks, the debate about their structure, and the amazing tools scientists are using to study them. Now, I'm curious about the bigger picture. What do pentaquarks tell us about the universe as a whole?
Well, remember that the Standard Model has been our go-to theory for particle physics.
The one that describes all the fundamental particles and forces, right?
Exactly. And it's been incredibly successful. But pentaquarks weren't part of the original plan.
So are you saying the Standard Model is wrong?
Not necessarily wrong, but maybe incomplete. Pentaquarks are making us rethink our understanding of the strong force, the one that holds quarks together.
So what's wrong with our current understanding?
Well, we used to think quarks only like to group together in pairs or triplets, mesons and baryons. But pentaquarks show us that the strong force has some hidden tricks up its sleeve.
Like it's been holding out on us all this time.
Exactly. And by studying pentaquarks, we can learn more about the strong force, its strengths, its limitations, all the different ways it can bind quarks together.
And this knowledge could have implications beyond just pentaquarks, right?
Absolutely.
For example, it could help us understand neutron stars better.
Neutron stars, those super dense collapsed stars.
The very same. The conditions inside a neutron star are so extreme, it's mind-boggling. And there's a good chance pentaquarks could exist in those environments.
So, studying these tiny particles here on Earth could help us understand what's going on in these incredibly massive and dense objects light years away.
You got it. It just shows you how interconnected physics is. What we learn about the smallest particles can tell us something about the largest objects in the universe.
Okay, my mind is officially blown again. So, the discovery of pentaquarks, it's not just a curiosity, it's a gateway to understanding some of the most fundamental forces in the universe.
And who knows, maybe even discovering entirely new forces or particles we haven't even imagined yet. It's like we've just scratched the surface of what's out there. Now I can't wait to hear about the future of pentaquark research. What exciting discoveries might be just around the corner. We're back and ready to wrap up our deep dive into the wild world of pentaquarks.
Pentaquark research? Oh, it's just getting started.
That's what I like to hear. So where do we go from here? What's next for pentaquark research?
Well, think of it like this. We've discovered a new continent, right? Pentaquarks, they've opened up this whole new territory in particle physics.
And we're ready to explore.
Exactly. And there's so much to explore. One of the biggest mysteries is still that internal structure, right?
Hmm.
Are they true five quark states? Or are we looking at baryon meson molecules?
Right, that's the big debate. And you've mentioned the electron-ion collider, the EIC, a few times now.
Oh, the EIC. That's going to be a game changer for sure.
I'm sensing a theme here. What makes the EIC so special for studying pentaquarks? Is it really that big of a deal?
Oh, absolutely. The EIC, it's all about precision. Imagine you're trying to take a picture of something incredibly tiny, right? You need a really powerful microscope.
And the EIC is that microscope.
Exactly. It's going to let us smash electrons into protons and neutrons with incredible accuracy. We'll be able to see the internal structure of these particles like never before.
So we'll finally know for sure whether those five quarks are really bound together or just hanging out in a loose molecule.
The EIC should give us the answer. But some people might wonder, why bother? Why spend all this time and money studying these tiny particles? What's the practical use?
It's a fair question. I mean, pentaquarks seem pretty far removed from our everyday lives.
They do, but you have to remember that basic research, it's driven by curiosity. And that curiosity, it often leads to unexpected breakthroughs.
So we may not know the practical applications of pentaquark research right now, but that doesn't mean they won't exist in the future.
Exactly. Think about electricity or quantum mechanics. Those started as purely theoretical ideas, and look at the impact they've had on our world.
It's amazing to think that something as abstract as pentaquarks could someday lead to new technologies or even solve some of the world's biggest challenges.
The possibilities are endless. And in the meantime, while we're waiting for the EIC to come online, theoretical physicists aren't just sitting around twiddling their thumbs. They're busy refining models, trying to explain how pentaquarks fit into our understanding of the universe.
And those models, they're not just about pentaquarks, are they? You mentioned earlier that they could help us understand things like neutron stars.
Oh, absolutely. Remember, neutron stars, they're these incredibly dense objects. The conditions inside them are unlike anything we can create here on Earth.
It's mind-boggling to think about the kind of pressures and temperatures that must exist inside a neutron star.
It is, and it's very likely that exotic particles like pentaquarks could exist in those environments. Maybe they even play a role in the structure and behavior of neutron stars.
So we're not just studying pentaquarks for the sake of it. We're trying to understand some of the most extreme environments in the universe.
Exactly. It all comes back to the idea that physics is interconnected. What we learn about the tiniest particles can have huge implications for our understanding of the cosmos as a whole.
That's what I love about physics. It's a constant reminder that there's so much more to learn, so many mysteries left to uncover, and who knows, maybe someday one of our listeners will be the one to make those groundbreaking discoveries.
Now, wouldn't that be something? It's been a pleasure, diving into the world of pentaquarks with you.
The pleasure was all mine. And to our listeners, thank you for sending in your research and for joining us on this incredible journey. Keep those questions coming and never stop exploring the wonders of the universe. Who knows what you might discover?